All right, so at this point what? You can distribute the negative 9 back through the parentheses. So if we distribute the negative 9 through the parentheses, we're going to have negative 9 and then x plus 2/3 squared, and then negative 9 to here plus 4, right? Like that. Okay, so let's go back over here and take a look at what we've got. God, all this crap that comes up in the background, I swear. So this integral becomes, let's bring the 7 out. 7, 1 over the square root of, now I'm going to choose to do something here. I'm just going to flip the order of this. I'm going to go 4 minus 9. And then in parentheses, x plus 2/3 squared dx. Is that fair? All right, now that looks a whole lot like, I mean, you have to squint your eyes quite a bit, but this looks like a squared minus x squared, right? Not quite though, because of the 9, right? Like if that 9 was a 1, then that would look like a squared minus x squared, but the x is a linear term and that's okay. Do you agree with that or no? No? I'm looking at you because you asked. If we had this, we would be able to do a trig substitution. Now this x right here couldn't be any linear expression because I could always make a u substitution. Like I could do u is equal to x plus 2/3. Then du is dx. So you'd rewrite this whole thing and it would become like 4 minus 9 u squared du. Is that okay? So the 9 is the only problem, okay? It's like I have a 9 right here. So how do we get rid of that 9? Just pull it out, right? So earlier, before I completed the square, I had negatives on both terms. But now, because I completed the square, I have a positive term and a negative term. So when I pull a 9 out, I can pull a 9 from here and a 9 from here, and that 9 can come out of the integral. I mean, not out of the, well, yes, out of the root and then out of the integral. That makes sense or not?
Yeah.
Okay. So integral 1 over, so let's pull a 9 out. When we pull a 9 out of the 4, we get 4/9. Then we pull a 9 out of the other one, we get this. Now that 9 came out of both of these, and then the 9 came out of the root. And when it comes out of the root, it's going to be a 3, because you have to take square root of 9. So that 3 is going to, right? And that 3 is going to come out here, and it's going to be on the bottom, so 7/3. And then at this point, you can do, is that okay from here?
Yes.
Okay. So that's it. Make sense? Okay. Now, let me address a question that was brought up by 2 students. And if you could, and I looked for, you sent me a thing about a video, right? Did you send me, someone sent me a request about video for partial fraction? I looked and I couldn't find it. It looked like my pre-cal class, that video got cut in half or something. So I wasn't able to send you anything. I'm sorry I didn't respond. Okay, so let me show you. There was a question brought up, and I believe this was the example that you had asked about. So if you could look in your notes, make sure that you have the same thing written here. This was, when we were doing trigonometric substitution, this was the last example I did in class. And this was the problem. This looks a lot like the one we just did in some sense, right? We had a root, and then we factored a 4 out. And when we pulled the 4 out, it came out of the root. When we pulled this 4 out, it came out as a 2, but then it had to get cubed, so it came out as an 8. Okay? And then we had this, and that's where we set up our trig substitution. So the trig substitution for this is that x will be a tangent theta, and a here is 3/2. So this was the trig sub we did, right?
Yeah.
Okay, and then from that, we know automatically from the formula that the square root of x squared plus 9/4 should be equal 3/2 secant theta. And then we take derivative of this, we get this. So I want you to ignore the part in red right now. Just follow the stuff that's in black. We went and we worked the problem out, and then at some point we had to do a reference triangle. And we based the reference triangle off of this piece of information. So if you take this information, You multiply both sides by 2 and divide by 3, you get this equation. And that's what you set up your triangle on. Tangent is opposite over adjacent. So that's this. And then to set up this, to get this side, you just use Pythagorean. So that was all good, right? Okay. So if we look at this triangle, we ask ourselves, what's secant theta? Because somewhere in the answer we needed secant theta, I guess. So secant theta would be the reciprocal of cosine. So it should be this over this, right? That right there. Okay. Now, this is what was brought up by the students. Secant theta is right here also, right? So instead of using the triangle, what if we had gone here to get secant theta? We would get the same answer. And that was the question, right? Is it the same thing? So if I solve this for secant theta, right, I multiply both sides by 2 and divide both sides by 3, and that's what's in red here. So we get secant theta as this. Isn't that what you had exactly? 2/3. Did you get 2/3 then root this?
Yeah, so I have 3/2 secant theta from the notes.
Yep, right here.
Yes. And so that just doesn't match up with the triangle.
Okay, well, but it does. You just have to.
He's moving over the 3 halves, multiplying to the other side, right?
Yes. See, because this is secant theta is this, right? Okay, this is 3/2 secant theta. So to get secant theta, I have to multiply both sides by 2/3. So if I multiply this side by 2/3, I get this, right? So secant theta is this. Now this may not look like this, but it is. Because if you force the 2 back into the root, just the 2, it gets squared on the way in, becomes a 4. And so you get 4x squared, and then when it distributes here, you get the 4 and the 4 to cancel, you get 9. So you got this part, right? And then the 3, don't push it in the root, just put it underneath the root, and then you're at this. So it's the same thing. It looks different, but it's the same. Does that resolve it?
Yeah, if it had been sine, though, there's like an x missing, right?
If there's sine, what?
Like if you did sine of that triangle.
Yes, this over this?
Yeah, and originally it had been like 3/2 sine, so it went to cosine or something, and you'd be missing the x, wouldn't you?
Well, for this trig sub, it's not sine, though. We would have to look at a different example, I guess.
Okay.
So let me see that one. Yeah, that was the one. Can I see it? Okay, let me look at this one. Okay, so for this one, I'm just going to write it down because I really want to make sure we address this issue and that we're not having any problems with it. So this was the problem, and so what we did here is the same thing. We pulled out a 4, and it comes out as a 2 on the outside, and then that gives us 3/4 minus x squared dx. And then we make the trig sub of root 3 over 2. This is a, right? So the square root of that principal root is, and we're using sine theta. And then by the formula, we know that 3/4 minus x squared should be equal to root 3 over 2 cosine theta, right? That's just by the formula. And then the dx will be root 3 over 2 cosine theta d theta. Okay. Yes, that. All right, now let me draw the triangle. If I draw the triangle from this, I have to multiply by 2 and divide by root 3. So sine theta is 2x over root 3. And then this side over here should be that squared, right? Minus that squared. Like that, right? So I think this is where you're asking. If you do cosine, right? Cosine is this over this, right? So cosine theta, or do you want me to do sine?
Well, so
Let's do cosine theta first. Root that over root 3, yes? Like that? Okay, now, according to this, this is what cosine theta is, right? So I have to multiply 2 over root 3 here. Yes? And now if that 2 goes in again, right, you're going to get the 4 to cancel. You get 3, and then you get the 4x squared, and then the root 3, you can just leave it on the bottom. So same thing.
okay.
You see it?
Yeah.
I don't know why I didn't see that when you asked it originally.
Okay.
Also, like when we were in the math lab and we asked about it, they so then it freaked us out.
Yeah, no, it's the same expression. It just looks different, right? Do you agree now that it just looks different? So when you first approached me, I don't know why my brain wasn't functioning properly or something, but I don't know why I didn't see that. I thought we were off by 2. I didn't realize we actually had the root 3 in there, so something didn't fire properly. So it's all good. Don't worry. The math universe is still being held up pretty solid here. Okay.
Man, I thought we were going to get Nobel Peace Prize.
Yeah. All right. So now today, what are we doing? Partial fractions, right? So we spent all last class just preparing for it, and now we get to do it. How many of you have your Texas Instrument calculator? How many of you do not have a Texas Instrument calculator? Raise your hand. It's okay. I need to know. Just one? So everybody in 2? Anyone else? So just 2? You do not need to go buy one. I will provide a couple of them for the test, all right? Because there's something we're going to do in here that's going to need you're going to want your calculator, all right? You're not going to want to have to do it by hand. So everyone who has a Texas Instrument, is it a graphing? Anyone not have a graphing one? Everybody has a graphing one? Okay, so we should be okay then. All right, 6-3. It's okay if you don't have it on you now. Okay, just make sure you have it for you for the test. And the test is not next week, but the following week. All right, so blah, blah, blah. Let's see. We did all this. Let's just remind ourselves. If we said constant over linear, we're good. Constant over linear, we're good. Constant over repeated linear, we're good. Constant over repeated linear, we're good. Constant over quadratic without an x term in the middle, we can do that with a formula. If it's a constant over an irreducible quadratic, which means we cannot factor this quadratic, then we can do it by completing the square and then using, I don't know, something. And then a linear over irreducible quadratic. Do you remember this? Okay, that problem right there that was where I had to make something happen. I let u be the denominator, and the derivative of that was 8x minus 4, so I made the numerator look like 8x minus 4. Okay, so we have a way of doing linear over irreducible quadratic, and then we have a way of doing linear over repeated irreducible quadratics. So anytime we see an integral like any of those forms, we are good. Theoretically, we are good. So now we're going to do our partial fractions. So we talked about what rational functions were last time, right? We talked about the degrees. Yes? And we did the first problem here, didn't we? Right? So the strategy for integrating rational functions was to always compare the degrees, and that will determine if you need long division or not first. And then after that, we proceed. And we never really got to actually doing partial fractions. So here are the notes on how to do it, and I'm going to refer back to these. All right, so I'm not going to read through them because they just look crazy. And we're just going to go with our first example. So here, let's do this one. All right, so when you look at this, you're sitting there, you're taking a test, right? You're freaking out because it's a test. And you see that, and the first thing you should be thinking is this looks like a rational function, right? A polynomial divided by a polynomial. So you should automatically be thinking this is probably partial fractions, but you want to also make sure that I'm not trying to trick you. I'm not real big on tricking students, but I mean, just check, is the derivative of this that exactly? Or are you off by a constant? Like, what's the derivative of this? 6x squared? I have an x squared. What's the derivative of this? 6x? I have 2x. What's the derivative of this? 2. Is that going to work? If I let u be 2x cubed plus 3x squared minus 2x, du is 6x squared plus 6x minus 2, right? dx. Am I off by a constant? Can I pull something out of this to make it look like the top? No, right? I can pull a 2 out and I get 3, 3, and 1, but that's not going to match. And with a problem like this, you can't do that little magic thing that I did on the previous one, where you can kind of make the numerator look like the denominator. And the reason why is because you have 3 terms. So well, we might be able to, but generally speaking, you can't. Where in the previous problem that I did, you can do it pretty much irregardless. As long as you have a linear over a quadratic, you can always do that. Here you can't always do it. So
So 2 terms is okay?
linear over quadratic, yes. So this, I'm gonna just make sure that you know I wasn't about to get tricked on that. Because what if you could just pull a 2 out and match the top? It's just a basic substitution. You're done. Move on, right? Okay, so you don't want to spend 30 minutes on something that should have taken you 5. All right, so I'm just going to check that. Nope, no go. So I start running through the technique. First thing I do is check the degree of the numerator. It's 2. Denominator, 3. The numerator is smaller than the denominator, right, in terms of the degree, so I do not need long division. So that means I move to the next step, and this is where we're starting the actual partial fractions. So the next step is this. Just rewrite the problem over here without the integral. We are not doing any calculus at this point, all right? We're just going to do some algebra. And we're going to do partial fraction decomposition. So the first step for partial fraction decomposition is to completely factor the denominator. All right, factor the denominator. So you're going to have to remember how to factor, which you're in Cal 2, right? So you're all factoring masters. What's the first step of factoring? Always look for what? Greatest common factor. Do they all have something in common? X, right? So I can pull an x out. And then I'm left with 2x squared plus 3x minus 2, right? Now I look in the parentheses, that's a trinomial, it's a quadratic trinomial, and I hope that I can factor that. It does indeed factor. And I'll put it right here. X squared plus 2x minus 1 on top over x. So what is it? 2x here and x here. Minus 1 plus 2. Now look, going from this parentheses right here to that right there is of Math 1414 skill. All right? Now, I'm saying that because I realize factoring is always an issue. I mean, like it's always, no matter what. I'm in Cal 3, I'm teaching, I've got students linear algebra, they still can't factor. So you need to be able to factor that, all right? I'm not going to spend any time on how to get from here to here. All right, now, once we're here, I hate saying that to students, like you need to know that, but it's true, you need to know that, all right? So, I mean, at some point, right, I have to assume, like you can add 10 plus 10. Like I have to assume at some point you can factor. All right, so now, is it completely factored? We have a linear term, right? A linear term, a linear term, a linear term, right? Or a linear expression, however you want to look at those. There's nothing more I can do to that, right? You can't break that down anymore. So now we go on to the next step. I'm going to write that up here because it's way down there. Okay, once we have completely factored, we are going to recognize what type of factors we have in the denominator. This is a very important part because this actually dictates what we do next. We have to identify these factors, and I already mentioned what they were. This is a brand new marker. It looks like crap. Linear, 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 right? So what I have here are 3 distinct linear factors. So if you go back and you look at partial fraction decomposition, it says, hey, if you have n distinct linear factors, then you do this, all right? Now, what does the word distinct mean here for us? They're all different, right? Like this is x, this is 2x minus 1, this is x plus 2. I don't have x plus 2 appearing twice, right? These are distinct, they're all different. So what we do is we say, okay, this expression can be rewritten as some constant that I don't know, capital A, over the first linear factor, plus some constant that I don't know, I'll call it B, over the second distinct linear factor, plus some other constant C that I don't know over the last linear factor. So the idea from partial fractions is this, that we can somehow, we can figure out what this number is, what this number is, and what this number is, so that when you put all these back together with a common denominator and clean everything up, you should get this. All right? So we're going backwards from that to this. So don't we need to find out what A, B, and C are now? Okay? Does this ring a bell from partial fractions? Does this sound familiar? Okay, well, for each distinct linear factor, for each one, we create a term, and the term will be a constant over the linear factor. Okay? That's the idea. So let's go find A, B, and C now. If we can find A, B, and C, imagine now that this was a number. Let's say that was like 1 over x. Could you integrate that? Sure. Right? Constant over linear. What if this was like 1 over 2x minus 1? Same thing, constant over linear. You could integrate that, and you could integrate that. So you see how the partial fraction decomposition takes some very nasty thing that's difficult to integrate and kind of splits it up into 3 simple integrals instead. If we can make that jump from here to here. We have to be able to make that jump, though. All right. What do we do next? Yeah, so what we do is we're going to clear the fractions here. This is an equation, right? So if this is an equation, I need to, I can do anything I want in terms of like multiplying both sides by something, adding, subtracting, doesn't matter. So I'm going to multiply both sides by the common denominator, which is this. So I'm going to multiply both sides by this. So imagine I come over here and multiply, x, 2x minus 1, x plus 2 on this side. And then on this side, I have to do the same thing, right? Multiply this side by x times 2x minus 1 times x plus 2. And that is going to have to distribute through all 3 of these terms. So it's going to have to go here, here, and here, right? What happens on the left-hand side? Like, what am I left with? Just the numerator, right? X squared plus 2x minus 1 equals, and then on this one, good things should happen. When I'm done distributing this through, I should have no more fractions, okay? I should have no more denominators. I should just have stuff on the top. So imagine 1 over x, a over x being multiplied by this. That x will cancel, right? And these won't cancel. So I'll have the a never went anywhere, the x canceled, and I have these 2 terms. So I write that down, a, 2x minus 1, x plus 2. And then I distribute this thing to the b term. Nothing cancels the b out, right? The b's still there. Does the x get canceled out? No. 2x minus 1 get canceled? Yes. This one? No. So the x is still there, and the x plus 2. And then finally, when we distribute to the c term, here to here, the only thing that cancels is the x plus 2. So you'll have the c, the x, and the 2x minus 1. All right, I need to find what a, b, and c are. Now at this point, there's usually 2 different ways you can approach this. I'm going to show you both, all right? The first way I'm going to show you, when I'm teaching this, I tell my students that this way is like the short way. Okay, this is like the short, fast, clean way of doing it. And then the other way is the long way. And I know you're sitting there, why would I ever want to do the long way if I can do the short way? Well, the short way doesn't always work, okay? The long way always works. So let's start with the short method, all right? I'm going to call this method, let's call this the short method. Does anybody know the short way of getting this? Yeah, what you'll try and do is you'll go and you'll attack these one at a time. So like you start off by saying, I'm going to try and find a first. Okay? So to find a, what I'm going to do is try and preserve this term right here. And I'm going to try and eliminate these 2 terms. And so with this equation, we actually have some control over it. And we can choose. This is one of the rare times in math that you get to actually choose what you want to do. Like the problem is not telling you what to do. You get to actually choose. So I'm going to right now choose a value of x that will eliminate this term and this term simultaneously, but not eliminate this term. So what value of x could I pick that would kill this term completely and this term completely? 0, right? If x was 0, this would go away and this would go away, but this would not, right? Because 0 in here would not give you a 0. 0 here would not give you a 0. So now we get to actually make that choice. So I'm going to write down let. I love this. Let. That's me having control, right? I'm going to let something be. Let x be 0. Okay? Let x be 0. Now, if x is 0, rewrite the entire equation. Starting on the left side, rewrite everything. So when 0 is plugged in here, this is pretty nice, right? You just get -1. So this equation up here becomes -1 equals, and then this right here, we have a, now let's plug in 0 here. 0 here minus 1 would be -1, and then 0 here would give us a 2, and then plus, now we already know these are dead, right? These are gone. 0 plus 0. So they're not there. Who cares? But I'm just reiterating that these go away. And look at what's left. Clean it up a little bit. You have -1 equals what? That's a -2a, isn't it? And that's just a simple little linear equation in a. Just solve for a. Just get a is a half. Right? So we have what a is. So we're like 1/3 of the way. Right? Now we just go get b and then we go get c. So let's get b now, and you get to start over. Okay? Start from scratch. You get to go back to this equation. You get to have that little God complex where you just like, let it be. Right? So what are you going to let it be? Let's try and get the b term, so simultaneously kill this one and this one. So what you're really doing is seeing what factor does this term and this term have in common? They have the 2x minus 1, right? These two have the 2x minus 1 and the one in the middle doesn't. So how are you going to make this one go to 0? Yeah, just real quick, just do a little, I mean, you can do it in your head, but you can also just, settle a quick equation here. Solve this, because you want that to be 0, right? So just solve that, you get x is a half. So that's what you're going to have to let x be in order to make this work. All right? Make sense? Okay, so let's do that. A is a half. I'll come back to that later. So now you don't have to change your voice or anything. Let x be a half. And you rewrite the whole equation. Now, unfortunately, plugging in 1/2 is not as clean as plugging in 0 was, right? You're going to have some fractions and stuff in here, but, who cares? 1/2 squared, 1/4, plus 2 times a half, right, is 1. Minus 1 equals, now this one we know for sure is dead, right? Okay, that's dead. So I still have b and then times x, so I'm going to put in parentheses times a half, and then times a half plus 2. What's 1/2 plus 2? 5 halves? Okay, so that's 5 halves right there. And then what about this last term? It's gone, right? So 1/4 equals 5/4 b. And you can solve for b by multiplying both sides by the reciprocal. 4's cancel. What do you get? 1/5? B is a fifth. So A was a half. B is 1/5. And last one is C. Just by a show of hands, how many of y'all have done this method before? Okay, so a lot of you have seen this? Okay. It's really convenient and nice because you can just kind of pick them off one at a time. A, B, and C. Go get them. All right, let's go get C. So to get C, we look at the A and the B, and we see what they have in common in terms of factors, which would be the x plus 2, right? So you've got to kill off that x plus 2. So you're going to let x be -2. Let x be -2. There was this game when I was a kid that I played a lot on this computer because there wasn't even a joystick or anything. It was just, all keystrokes and stuff. I don't remember the game, but I remember there was like this, you could go into God mode in it, where you just had all the weapons, all the money, everything, you know? And what you do is you type into the keyboard, make it so. That's what you, make it so. And then all of a sudden you went into God mode. So that's what we're doing here, like, make it so.
You don't know what the game was?
I don't remember the name. Was it what? No. It was a PC game, old school. I mean, we're talking old school. I don't remember the name. I mean, maybe if someone said it, I would know, but. Okay, negative 2 squared, 4. Plus 2 times negative 2, minus 1, right? All right, and then we know the A term and the B term are both gone. So I just got to plug in negative 2 here. So C times negative 2, and then be careful here. We have 2 times negative 2, which is negative 4, but then minus 1, it's negative 5. The left side's negative 1, and the right side is 10C. And so C is negative 110. Now we're not done, okay? All we've done is the partial fraction decomposition, right? So this is now going to allow us to rewrite our integral. But I shouldn't have erased that, but oh well. I'll come back to it. All right, here's the integral. This integral becomes a new integral, right? And it's actually 3 different terms that I'm going to integrate. The first one was a over x, right? A over x. So that's a, right? So watch how I write this. It's going to look weird, but just do it. It's 1/2 over x, right? That's a over x. Plus b over what? And you've got to get these in the right order. 1/5 over, it was the 2x minus 1 factor, right? And then the last factor on the bottom was the x plus 2. So that's going to be plus negative 1/10 and then x plus 2. So notice I put pluses in between all of them, even though this one was negative. I didn't put like negative out here. And also I just left those little fractions up on top, right? I could have written this as 1 over 2x. I could have come here and put the 5 through here. I could have put the 10 through there, but I didn't, okay? And that's because I'm about to integrate, and what happens with constants when you integrate? They can come out, right? So that's exactly what I'm going to do. So when I integrate this one, I pull the 1/2 out, and then I integrate 1 over x, which is ln absolute value of x. All right, plus, now this one I'm going to pull the 1/5 out, right? And now I really have 1 over 2x minus 1. And what's the antiderivative of 1 over 2x minus 1? Drum roll. 1 over a ln of, exactly. So you have to, remember we have a 2 here in front of this linear thing. So we have to compensate for it, 1 over 2 natural log of 2x minus 1. That's why we did this last class. I showed you, what happens if you have a constant over a linear expression. We did a couple of examples, and I said, look, we've got to account for this a here is a 1 over a out front. And then the next one, the negative 1/10 comes out. And again, if we pull the negative 1/10 out, we have a 1 over linear, right? Constant over linear. And here, this is a 1 in front, isn't it? So you don't even need to compensate for it. So it's just natural log of x plus 2 plus c. And other than putting these two together and making that a 1/10, we're done. It's kind of nuts that the antiderivative of this is something so kind of simple. I mean, natural logs in there, right? It's kind of odd, but that's what happens. So if you took if I were to check my work, which I'm not going to, I would take the derivative of this and I would get back this, right? But to get back to that, I would actually have to put these together. I'd have to get a common denominator and kind of compress them back into one term. All right, that was the short method. We're going to do the long method. All right, so the long method.
So does that just mean do long method every time?
It's up to you. I don't care.
You said short method won't work.
I'll show you the next example. The short method won't work. So that'll give you an illustration. You'll know when you look at what you're trying to do whether or not it's going to work. Okay? So let me go back. The method starts when you've got it down to this right here. We had that equation we were working with. X times 2x minus 1. Just double check, make sure. I'm pretty sure that's right. That's the equation that we were kind of playing God with, right? Are they? You sure?
No. That's right. You're good, you're good.
I'm good? Okay. All right, so that was the equation, right? And I said, hey, at this point, we need to solve for A, B, and C, and we could do short method or long method. Okay, so you saw the short method. The short method, what tells us we can use the short method is a quick mental check. Like, can you get the A term? Can you kill both of these off without killing this one? So we said, yeah, x is 0 will kill that, right? And leave this one. And then when you go for B, can we preserve this and kill these two? And we said, yeah, because these have 2x minus 1s in them, right? And this one doesn't. And then here to kill this, or to leave this one, we need to kill these two. So these had x plus 2, and this one doesn't. So that short method would work. However, if you wanted to do the long method, this is how the long method would work. What we have to do, and this is kind of very strange, we're going to actually multiply all of this out. Like we're going to expand and multiply it all out. All right, so let me start with this. If I distribute here to here, what do I get? 2x squared, right? But then I'm going to multiply it by a. So I'm going to write 2ax squared. So I put the actual number first, then the a, then the x squared. That's just the way I chose to write it. Now when I do here to here, what do I get? 4x. And then this to here, minus x. So that's really going to give me a 3x, right? And then I have an a. So plus 3ax. That's the middle term. I kind of did them together. And then the last term would be what? Minus 2 here, but then times a, so minus 2a. All right, so I've multiplied out the first term. Plus, now this one's not as bad because it's bx, right? It's not, two terms, not a binomial. So we can just go here and be done. So we'll get what? Bx squared plus 2bx. And then the last one, plus, I go here to here, here to here. Same thing. I don't have to worry about foiling or anything like that. So what is this? 2cx squared minus cx. Now we're going to do something kind of interesting. We're going to take all of the terms that have x squared in them. See those? And we're going to just move them next to one another. Like, because this is addition, so you can move things around, right? Addition, subtraction, so we can move things around. So I'm going to put this one, and I'm going to put this one next to it, and then that one next to it, all right? And when I do that, recognize that they would all have an x squared in them, wouldn't they? And because they all have an x squared in them, I'm going to factor the x squared out. So watch what I write next. I do parentheses, 2a plus b plus 2c x squared. Now, the x squared that I pulled out, I factored it out. I didn't pull it out to the front, did I? I pulled it out to the back, but that doesn't matter, right? I mean, because if I distribute that through, I still get it, right? There's a reason I did that, and I'll illustrate that on the next step. Okay, the next one, I'm going to look at all the x terms. There's an x term, there's an x term, and there's an x term, right? Bless you. I have 3 x terms there. So I'm going to put those all together and then factor out an x, and I'm going to pull it out the backside. So I'm going to say plus, and then parentheses 3a plus 2b minus c, and then here's the x that was in all of them, right? Are you all following that? Yeah. Okay, all right. And then I'm going to look finally for anything that doesn't have x, right? I got all the x squareds together, got all the x's together, now anything that doesn't have x. And there's only one of them, right? Right there? And so I'm just going to slap that out here on the outside. Okay. Now let me try and explain why it is that I pulled the x squareds out the back, or the x's out of the back side of the parenthesis instead of out the front. The reason is because this is an equation, right? So we have to have balance. Like the left side has to be equal to the right side. So if I look at my left side and I look at the coefficient on x squared, the coefficient is a 1, right? So whatever the coefficient is here on the x squared must match up with the coefficient that's on this x squared. Because, right, all of these are numbers. So if you put them all together, you're going to get a number in front of x squared. That number has to be 1 in order to maintain the balance, right? Yes? Again?
So whatever's on the inside has to be.
Yeah, whatever's here. Do you agree that A, B, and C are supposed to be numbers, right? I don't know what they are, but they're supposed to be numbers. And if I were to put them together, I would have a number in front of x squared. In order for this equals to hold, whatever's in front of x squared here would have to match up with what's in x squared in front of x squared here. So 2a plus b plus 2c must be 1 for that to happen. And then I look at the next piece. I have a 2, right? A positive 2 here. That's in front of x. That has to match with what's in front of the x over here. Right? And then the stuff without an x, this negative 1, has to match up with whatever doesn't have an x here, which is negative 2a, right? So what we have now are 3 conditions that must be met, right? This must be 1, this must be 2, and this must be negative 1, right? We have 3 different equations, and we have 3 unknown variables. So what we're going to make now is a system of equations from college algebra. System of equations? Let's do it. Yes, the long method is going to require that we solve a system of equations. All right, so let's write down the system of equations. When we do systems of equations in college algebra, we usually do a large brace that tells everyone about to give you a system of equations. And here are the equations. I know that 2a plus b plus 2c must equal 1, right? That was that. I know that 3a plus 2b minus c must equal what? 2. And finally, I know that negative 2a must equal negative 1. So there we go. 3 equations, 3 unknowns. Now, you could look at that right now, and you could actually figure out what A is, couldn't you? Right? A is going to be just this, just solve. You get A is a half, right? But you still need to go find B and C, don't you? And what if this back here was a lot more complicated, like negative 2a plus b minus 4c, right? Then you'd have a true, legitimate 3 equations, 3 unknowns, right? So the question is, how do we solve that, right? How do we solve that? It depends, right? It depends on what you've learned. But that's why I asked you how many of you have your calculators, because we're going to use our calculator to solve it. All right? Why are you saying, oh, you want to do it by hand? Oh, you don't have it with you. You bet you have one, right? Okay, all right. Well, then just look along with your neighbor. So who does not have one again? There and there. So you have no access to a graphing one. I don't want you to buy one, but you don't have access to one. A friend, any? Maybe you can just look, see if you know. If not, like I said, I'll provide them, but only for the test, which means that I don't want that to be the first time you're using it. You know what I'm saying?
What type of? I would say, what type of calculator do you provide? Because I know they've linked them out.
I have like a TI-84. Yeah.
Which they linked out on MathLab.
Yeah, and we can also check them out in the math lab with student ID. Okay, you ready to get started on this? Let me make sure you understand what I'm about to tell you. We could solve this by hand. It would take us probably, well, this one's not too bad. This one might take us about 5-10 minutes to do. But if we had all like B's and C's in here, this may take us about 15 minutes to solve. So the calculator, we're going to use it as a tool here, especially because later on in other problems, like in the homework, you might actually get a system where you have like 5 unknowns and 5 equations. And that's something you don't do in college algebra, right? You stop at 3 unknowns, 3 equations. Yes? All right. So, what are we going to do on our calculators? I already see people punching away there. All these calculators are a little different, these different models, okay? Like the TI-83 is a lot different than the TI-89, right? So what I'm about to do is I'm going to show you a method for doing this that will work on all the calculators. If you have a way of doing it already that you're happy with and you know how to do it, then do it, okay? I'm not here to reteach it. But if you've never done this and you want to know how to do it on all calculators, follow my instructions here. First thing we're going to do is we're going to rewrite this system of equations using a matrices. Now that doesn't really make that much of a difference. It's just to get you acquainted with what a matrices is, or what a matrix is. And all it is it's the system of equations written without the letters. So, you have, like, this is our A column, B column, C column, and then over here is our equals whatever the number is. So you have to make sure this is in the right order, and then you just write the coefficients. 2, 1, 2, and then equals 1. So I'm just pulling all the coefficients here and putting them in a row. And then I do it for the next one, which would be 3, 2, -1, 2. And then the last one, what would my last row be? 2. -2, 0, 0, -1. Okay? So even though it's not written here, these are our A's, our B's, our C's, and this is our equals and number. This is called an augmented matrix. That's not important, but that's what it's called. All right? Now, let's solve this. How's the calculator going to solve this? Well, what's going to happen, and let me just show you what's going to happen. We're going to do something on our calculator that's going to take that matrix and it's going to spit out an answer, and the answer is going to look like this. That's what it's going to do. And I'm saying to you that this is the answer for A, B, and C. Now, why? What is this equation? If I told you to rewrite it back in this form, what is this equation on top saying? A, nothing, nothing, equals some number, right? This one is saying B equals some number, and this one is saying C equals a number, right? So the question is, how do we go from here to here? Well, that's what the calculator is going to do for us, all right? But the way you see this with the ones across here, or across the diagonal, and zeros everywhere else, when you can turn a matrix from that into this is called a very special, this has a special name. It's called reduced row echelon form. I think I spell echelon right? Echelon?
E-C-H-E-L-O.
Yeah, echelon. Okay. Reduced row echelon form. That's what this is called. So we want to turn this matrix into its reduced row echelon form. Got it? So what we're going to do is we're going to go to our calculators now. All right? And we're going to, somewhere on our calculator, we're going to find what's called the matrix menu. So everybody who has their calculator, find your matrix menu. I'll give you a second. If you can't find it, let me know. Got it? Everybody find it? Up along the top of the screen, you should see something that says like names, math, and edit. Something like that. Everyone there? Okay, so what you want to do now is you want to select math. So what you're doing is you're telling the computer, you're saying, hey, look, I'd like to do something with a matrix, all right? What would you like to do? I'd like to do some math with the matrix, all right? Now, what kind of math do you want to do? Well, there's a whole list of things you can do, right? Scroll down until you get to, what do you think? What? What is it? Nope, not augment. Keep going, keep scrolling. RREF. RREF is what you want to find. Now be careful because there's an REF. Not REF, RREF. And what does that stand for? Reduced row echelon form, right? That's what you're going to tell. You're saying, hey, I want to do reduced row echelon form on a matrix. Got it? Hit enter. All right, and now what you should be looking at is it should have sent you back to the home screen, and you should be looking at, your home screen should say RREF, and there should be a parenthesis. So what you've done is you've called up the RREF routine, the program. You've called that program up, and it's going to execute it, but you have to give it some input, right? You have to give it the matrix, which I've now erased. 2, 1, 2, 1. 3, 2, negative 1, 2, negative 2, 0, 0, negative 1. Okay, so the question now becomes, how do you put that matrix into the calculator, right? How do you do it? So here's how it's done. You all ready? This is very important. Syntax, that's typing the right things in. RREF parenthesis. Here we go. Bracket. The first bracket is telling your computer, here comes the matrix, all right? It's saying, I'm starting the matrix right now. That's what that first bracket means, all right? Next thing you put in. Everyone find their bracket key? Not parenthesis, bracket, yes? Okay, next key, bracket again. This is telling your computer, here comes the first row, all right? So the first bracket was, here comes the matrix. Second one is, here comes the first row. Now, what is our first row? 2, 1, 2, 1, right? You have to put commas between these numbers. 2, comma, 1, comma, 2, comma, 1. Now your comma key is somewhere on there. You'll have to find it. So just so y'all know, there are easier ways on some of these calculators to put a matrix in. And so that's why I'm saying, please remember, I'm trying to give you a way of doing this that works on all of the TI calculator platforms. You just call up the function and you put the matrix in this way, all right? Okay, so now what do you think you do next? Close the bracket. Close the bracket. That closed bracket is telling you, I'm done with the first row. Then what do you think comes next? No comma. Yeah, I know. It seems like there might be a comma there, right? New bracket. It's the proper syntax for TI. Yeah. All right, so here we go. What do you think comes next? 3, comma, 2, comma, negative 1. Be careful. Make sure you use the negative key and not the minus key. Comma 2. Close bracket. Open bracket, negative 2, comma, 0, comma, 0, comma, negative 1. Close bracket. Close bracket again. Now that last close bracket closes off the matrix, right? One more thing. Close parenthesis closes off the function. Enter.
You messed it up.
Okay? It should be presenting you with something that looks like this. 1, 0, 0, then probably 0.5, right? And then 0, 1, 0, 0.2, and 0, 0, 1, negative 0.1, right? Like that, right? That's what it should be giving you. Now you should be able to interpret what 0.5 is as 1/2. How do you convert 0.2? How do you convert 0.2 to 1/5? Other than maybe you just knew that. Isn't this your tenths? So isn't that 2/10? It's 1/5, right? This is negative. Isn't this just 1/10? Well, that's 1/10, right? 5/10 is 1/2. So if you reduce these fractions, you get back to those. Plus, there's probably a key on your calculator where you can go from decimal to fraction. So,
I know the decimal function, but do you know how to pull that number out?
what do you mean?
Because I have the matrix there,
Mhm.
or the answer.
Mhm.
And then I know how to, if I put 0.5 into the calculator, I know how to go to turn that into a fraction. How do I pull that 0.5 by itself? Like say it's like 0.270, something like that.
Like, how do you select just that entry? You'd probably have to call up another function that pulls out the like ith column, jth row or something. But I'm not sure why you'd want to do that. I mean, you can just look at it and, right? No?
Or something like more complicated.
Like it was a more complicated decimal?
Yeah.
Yeah. I would expect to see, like on a test, I would expect that the decimals that come up here are going to be common decimals. Like I don't think if you get like 0.3476192, right? I would be concerned that perhaps you did something wrong. Yeah. All right. What do y'all think of that? Okay, so now with that sort of input, when we did this first bracket for the first row, theoretically we could have as many rows as we want and as many numbers as we want. So if we had 40 equations and 40 unknowns, we could actually call up this algorithm, right? So it's a pretty powerful algorithm.
Please don't put 40.
I'm not. I'm saying like off on the side as a side note, you can now, with your calculator, you can solve a system of n by n equations, n unknowns, theoretically on that, right? For a different class, maybe not necessarily this class, but a different one. Okay, so that's the long method. We arrived at the same result. We go back, get the answer, we're done. Are y'all ready to do another one? All right, let's do it. All right, so we look at this one. We need long division first. Long division first. So we start with long division. We put x to the fourth plus 0x cubed. I forgot to ask if anyone had any questions on that calculator thing. Was everyone able to get it? Anyone have any problems with it? Everyone was good? Yes? Okay. So I'm writing the numerator in the division box, and I'm putting in a 0x cubed to account for that space that I have, right? That missing term. And then on the outside, I put the x cubed minus x squared minus x plus 1. And then we just play our little game here. What do you multiply x cubed by to get x to the fourth? X. And so that x will now distribute to each one of these. X to the fourth minus x cubed minus x squared, and then plus x. And then once we do that, we change all the signs, right? All positives become negatives, negatives become positives. So that becomes a minus, this minus becomes a plus, this minus becomes a plus, this plus becomes a minus. All right, so what do we have when we start adding down here? Not 2x, just x cubed, right? Because that was 0x cubed. Minus x squared.
Minus 3x.
Plus 3x?
Yeah.
Right, plus 3x plus 1. And then we go again. What do we multiply x cubed by to get x cubed? 1. So plus 1 here. And when you multiply that times 1, it's just the same thing over, right?